This is my week 12 assignment for thermodynamics. So we have the following regen and reheat ideal Rankine cycle shown here. I don't need to read all the values because we're going to go through them later, but they're all given, all the ones I need. The bleed pressure is not from an intermediate point in the high pressure turbine. It all leaves together at the end of the high pressure turbine, and then it bleeds out from here. I wrote it in green so that it can be seen better. And then besides that, it's all pretty much the same as we would expect. So then the TS diagram, I anchor it with these three pressure lines. There's the P equals P1, so that's the pressure before and after the condenser. There's the P7 equals P6 equals P2 equals P3, they're all the same. 0.8 megapascals, that's because it's an open feed water heater, so that has to be all the same pressure you're mixing in there. This pressure is the same, 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 and it leaves as the same pressure as well. And finally, P5 equals P4, the pressure before and after the boiler before it enters the high pressure turbine. These processes are all isentropic because it just says that it's ideal, and it does not say that we have to factor in for the isentropic efficiency. Assumptions: pumps and turbines are isentropic and adiabatic. Outlet of pumps is incompressible saturated liquid. Pressure changes through boiler and condenser are negligible. Every device is steady state control volume. Neglect changes in KE and PE for the process. So then let's try to quickly go through the states. So define state 5, that's after the boiler. It's just a table lookup at superheated vapor at the given pressure and temperature. State 6, we have the entropy because 5 to 6 is an isentropic process, referring back to our TS diagram. We compare that to the SG at that table value, 0.8 megapascals. We find that we have to interpolate at superheated vapor, find the H6. State 7, 0.8 megapascals, 500 degrees Celsius. It's a superheated vapor because it's after the reheat, we have H and S. State 8, this is before the condenser. Again, it's an isentropic process, isentropic compression. We find that it's between SF and SG at that pressure, so it's saturated mixture. Find X, use X to find H8. Then after, we know that it's a saturated liquid as it leaves before it goes in the pump. We take note of the VF because we need it for later. We find the H1, the S1 from table lookup. Then this is where we need the VF for because it's isentropic adiabatic pumping. The delta H is equal to V delta P, so H2 equals H1 plus V delta P, the VF from before. We find that. State 3 is 0.8 megapascals, saturated liquid again, and again we take note of this for later. We look it up at tables at that pressure and saturated liquid. So then we have, for C4, we have the pressure. It's again isentropic, so we have the entropy. And then we use H4 equals H3 plus VF from before, delta P. Now we have all the states. So with all the states, we can now find the entropy for the reheat and the regen. That's what this question is really asking for. So for the open feed water heater, we need to find the Y. And so that's the mass flow balance, mass times energy. So M in H in minus M at the exit, H at the exit equals 0. So we have the YH6 plus 1 minus YH2 equals H3. We expand this, and then we factor with the Y. So we isolate for the Y. And because we found all the states from before, we can easily just plug and chug, and we have the Y equals 0.202, which is approximately in the range we would expect it to be in this Rankine cycle. It's usually not that much higher than 0.2, so that checks out. We also need the rest of the mass flow at the other junction. There's the part that bleeds out, which is 0.202, and the rest of it, which is 1 minus Y, so it's 0.798. Then we need to find the Q for the reheat process to ultimately find the entropy for the reheat process. So this is my governing equation. It's the first law. We cancel out the work because the boiler does not work. We isolate we rearrange, so that it's sum of the heat equals MHE minus MHI. And then, again, because we have we have all the numbers that we need, it's very easy. It's plug and chug. 1 minus Y represents the mass flow. Plugging everything in, we find the Q. We're given temperature at the boundaries, 1800 kelvins. So sum of QTB, again, going through this formula with all the values that we have, we get that the SGen for the reheat is 0.5899 kilojoules per kilogram Kelvin. SGen of the regeneration process, we can cancel this out from our second law immediately. So then it's just this, which is very simple. Again, this is 1 at the outlet because then everything is combined at the outlet of the feed water heater. One of the inlets is represented by Y, one of the inlets is represented by 1 minus Y. Plug everything in, and you get the SGen for the regen part through the open feed water heater of 0.162 kilojoules per kilogram Kelvin. Thank you.